Welcome to the talk. Our paper is Optimal Pricing of Information. This is a joint work by me, Weiran, and Haifeng. In this paper, we propose an optimal mechanism for selling information. And in the model, we consider there is one information seller and one information buyer. The information seller has data or the information which is valuable for the information buyer. So the seller can charge money from the information buyer by reviewing those information. For example, the credit report company has credit information about loan applicants, and the loan company can make a better decision based on those information. And in daily life, the car or the house inspector has better knowledge about the condition of a car or house, and they charge commissions from their customers for those information. Also, in financial market, investment investor knows better about the market, and they charge service fee from the client. So a natural question is about how to sell this information optimally. And in the model, we consider there is one information seller and one information buyer. The buyer is a decision maker facing a binary choice, a passive action 0 or an active action 1. The active action can be approving the loan, buying a house, or investing in a stock. Or the passive action will always derive utility 0. The active action will derive utility VQT, where T is a buyer's private type, and it is publicly known drawn from a distribution F and bounded by T1 and T2. So the seller knows the distribution F, but not the exact T. In here, Q is a random state of nature, which is unknown to the buyer, and publicly known drawn from a distribution G. Qt are assumed to be independent. So the seller can observe the realized Q, which is the information, but the buyer only knows the distribution G. Now, let's say a concrete example. In here, buyer is a loan company deciding whether to approve a loan or not. If not approving, the buyer will derive utility 0. If approving loan, the buyer will derive utility 1. In here, VQT will derive utility VQT. In here, VQT equals to Q times T minus 2. And we can understand it, the Q as a payback rate, and T is the gross profit from a successfully payback loan, and minus 2 is a company's operating cost. In the example below, where Q is known drawn from a uniform distribution from 0 to 1, and the realization of Q is 1 and T is 3. So from the seller's view, VQT equals to 1 times 3 minus 2, which is positive 1. However, from the buyer's view, since the buyer only knows the distribution of Q, the buyer will compute the expected utility T based on expected Q, and get a result of negative 0.5. So in this case, the buyer will reject the loan and miss a chance to make a better profit. So we can say information will bring values by getting to a right decision. And a natural question will be, will full revelation be the best revelation scheme? The answer is no, and based on our theorem, will only reveal whether Q is greater or equal to 2/3 is the optimal mechanism. And notably, this greater or equal to format is not a coincidence, and we actually prove that there always exists a threshold signaling mechanism that is an optimal mechanism. And when talking about optimal mechanism, a natural question is about which space are we considering. In this paper, we're considering the space of so-called generic interactive protocols proposed by Babov et al. In 2012, which is a very general class of mechanisms to sell information through signaling, and those mechanisms can be possibly interactive. Also, based on previous work, there always exists a revenue maximizing mechanism which consists of manual pi-t and pt. In our paper, pi-t is a signaling scheme with two signals, sigma 0 and sigma 1, where they result best buyer action 0 and 1 respectively. And pt is a payment from the buyer with type t. So we sell information through signaling, and the signaling scheme in our paper is defined as pi-qt. which models the probability of recommending action 1 or sending sigma 1 given Q and T. We made assumption on the buyer's utility function, where VQT equals to V1Q times T plus rho Q. This assumption is widely used in many literatures in cell information. In previous long example, where VQT equals to QT minus 2, we have V1Q equals to Q, and the negative 2 over Q equals to rho Q. So with the signaling scheme we defined earlier, we are ready to give the definition of threshold mechanism. A threshold mechanism PQT is called a mechanism PQT is called a threshold mechanism if there exists a function theta t, such that for all type t, if rho Q passes this threshold, the seller will set PQT equals to 1, otherwise PQT equals to 0. That means if rho Q passes the threshold theta t, the seller will always recommend action 1 to the buyer. Otherwise, the seller will always recommend action 0. We proposed mixed virtual value phi ct in our paper, and it is a linear combination of lower virtual value, which is the classical virtual value proposed by Merson, and the upper virtual value, which is different from 1 over ft from the lower virtual value. And our mixed virtual value takes c fraction of lower virtual value and 1 minus the fraction of upper virtual value. And I will explain it later in this talk why we have the mixed virtual value. In this paper, we use the superscript plus to denote the iron version, and we proved the lemma, which may be of independent interest, that the iron version of mixed virtual value is non-decreasing in C. Now we are ready to state our main theorem. Our main theorem divides all cases into 3 incidents. I omit some wording here because the optimal mechanism for each case has the similar structures. So for example, in case 1, where we have VT2 is less or equal to VL, the mechanism with threshold signaling function, theta star t, and the following payment represent an optimal mechanism. Where for the optimal mechanism in case 2 and case 3, they have exactly the same structures, but only differed by the threshold and this payment function. Now let's take a detailed look. The classification is done by VT2, VL, and VH. The definition of VL and VH can be found below, but we only need to understand that they are all constant. So given an instance, we can easily classify it by a simple calculation. For example, if VT2 is less or equal to VL, it is in the gray region in the graph, corresponding to case 1, and ditto for the other 2 cases. Recall the signal scheme PQT equals to 1 if rho Q passes threshold theta star t. And in each case, the theta star t corresponding to a different virtual value. For example, in case 1, theta star t equals to negative lower virtual value. And in the graph, we can see if rho Q passes the threshold, the seller will recommend action 1. Otherwise, the seller will recommend action 0. And same for case 2, which uses the upper virtual value. And in case 3, the theta star t will equals to negative mixed virtual value. And recall that we have VQT equals to V1Q times T plus rho Q. If the seller always wants a buyer to make the right decision, the seller will recommend the action based on T. However, it is not optimal it is proved to be not optimal in our theorem. And the last part is a payment function, and it is mainly used to ensure IC, IR, and obedience constraints. The proof of this whole theorem is intricate. For the interest of time, I would like to highlight 3 major steps. The first step is about the problem formulation. We formalize our problem as an optimization problem with functional variables PT, and the PT is also depends on PQT. So the goal is to maximize the revenue or the expected payment from the buyer. We have 3 constraints. The first is IC constraints. The IC constraints can be reduced to the standard format, but notably in cell information, if the buyer misreports another type T prime, the recommended action may no longer be obedience. Thus, we need a reduction to reach this IC constraint. And the next is IR constraints, which is the payment by participating in this mechanism minus the payoff by participating in the the payoff by participating in this mechanism minus the payment should be at least the payoff without participating in this mechanism. Where the obedience constraints can be reduced to a similar inequality. And by observation, we can find that if we have payments non-negative for all type T, IR will imply obedience constraints. And we proved the lemma that there always exists an optimal IC-IR mechanism where the payment is non-negative for all type T. So the payoff by participating in the mechanism in selling information will be the expected utility by following the recommendation policy. However, the key difference from selling physical goods is that in selling physical goods without participating in the mechanism, the payoff will be zero. However, in selling information without participating in the mechanism, the payoff will be max between 0 and Vt, where Vt is the expected utility by always taking action 1. That means if the distribution of Q is good enough, the buyer will take action 1 without purchasing any information and can derive a positive utility Vt. So to capture this big difference in IR constraints, we use the surplus function St to capture the gap between the left side and the right side of IR constraint. And to ensure IR constraint, we always want this St to be non-negative. Now we can visualize it that in selling physical goods, the St will first be 0 before the buyer gets the item. And after the buyer got the item, the St will be increasing as T is increasing. So we also want to capture the shape of St in selling information. And we proved the following lemma that St is weakly increasing from T1 to T bar and weakly decreasing from T bar to T2, where T bar is a private type that will make the expected utility without purchasing information equals to 0. Thus, a simple corollary is that in selling information, the buyer with type T closer to T bar will benefit more from participating in this mechanism. The next lemma is that a feasible mechanism must have either ST1 equals to 0 or ST2 equals to 0. An intuitive way to understand it is as if there is strictly a positive surplus, we can freely transfer it to the revenue without hurting the IR constraints. That means in a graph, we can move the shape of ST down until one of its ends reaches 0. Next, we characterize the feasible mechanism. We proved that these first two conditions are equivalent to IR constraints, and these two inequality are equivalent to IR constraints, and payment non-negativity is equivalent to obedience constraints. So we can derive the revenue function from the condition of the IC constraint, and we get the revenue function as following. By observation, we find that GQ, FT, and V1Q are all positive. So the way to maximize the first term is to set PQT equals to 1 if and only if rho Q is at least negative lower virtual value T. And the way to minimize the second term is set UT1 to its minimum possible value, which is 0. And it can be roughly understanding as set ST1 equals to 0. So if the shape of the ST curve is in this format, we successfully get an feasible optimal mechanism. However, if the shape of the ST curve is in another format, the mechanism is no longer feasible because ST is negative and our constraint is violated. Thus, to fix this problem, we derive the revenue function from another angle, where in the first revenue function, we expand from T1 and has the lower virtual value. In second revenue function, we expand it from T2 and has the upper virtual value. The way to maximize the first term is the same, and the way to minimize the second term is to set UT2 equals to its minimum possible value, which is VT2, and we can roughly understand it as set ST2 equals to 0. Thus, if the format of the curve remains the same, we successfully adjust the mechanism to be feasible and optimal. However, it is possible that if we look from the first revenue function, we lost control of ST2. If we solve it from the second revenue function, we lost control of FT1. Thus, we take a linear combination of those two expressions. which produce the same revenue. And this is the reason why we have the mixed virtual value, say lower virtual value plus 1 minus say upper virtual value. And in here, C is carefully picked to guarantee feasibility of the mechanism, where the feasibility proof is quite technical due to feasible constraints and irony procedure over its mixed virtual value. However, we can get an intuitively understanding from the graph, or in the instance of case 3, we have this curve if we look from the first rounding function. We have another curve if we solve it from the second rounding function. But by taking a linear combination, we get a new curve. This new curve has a nice property that by moving it up, the ST1 and ST2 will reach 0 simultaneously because the mixed virtual value C is carefully chosen. And thus, we successfully designed an optimal feasible mechanism. Thus, to wrap up, our paper proposed a closed form solution for the optimal mechanism in cell information. We also proved that there always exists a threshold signaling mechanism that is the optimal signaling mechanism. Next, we proposed the new concept of mixed virtual value and proved its irony property, which may be of independent interest. Thank you, and any questions are warmly welcome.